Okay, it's recording now.
Okay, great. Excellent. Can you all see the board? Those of you who are comfortable can turn your video on so we can see each other. So just in case if you have any questions, you can always, raise your hands. I can see you. And can you please send a note saying that you're present in the chat box so that I will have the attendance for this class? So send me in the chat box that you are present with your name. That will serve as my attendance for this class. Before I begin, I just wanted to know if you had a chance to review the materials that I posted on the Canvas. Yeah? Were you able to open my voiceover presentation for the atomic properties such as the sizes, electronegativities, we didn't talk about electron affinities, which we will talk today, and some of the calculations that might go well with the lecture. So before I continue, I wanted to know, have any questions on that material?
I have a question, Professor.
Yes.
I know you show the shapes of the dumbbells and like how they there are different shapes, but I didn't understand the probability of finding the electron. Is it between where they meet the shapes, or is it?
It's a good question. Okay. Let me explain that a little bit clearly. Suppose if you look at a p orbital, can you see the p orbital? All right, it's a dumbbell, right?
Yes.
So in this case, what happens is, 1 second, I think there are people who are waiting for. Just give me 1 second. So folks, those of you who joined this lecture late, that's 10 of you, could you please send a chat saying that you're present? So that will be the attendance for this class. For those of you who came just late, we are talking about what does the shape really mean in terms of the probability of finding an electron. Is that your question, Gurveer?
Yes.
Okay, so if you look at a dumbbell, right? So you have a lobe up and a lobe down. So those two lobes are joined at this point here. Now, if you look at the value of the wave function at the middle, that wave function is 0, which implies that the probability, which is square of the wave function, is 0. That means the most probable location of finding an electron is either in the top or the bottom. Okay, only difference between the top lobe and the bottom lobe is that the electron wave functions are not in phase. One is, in other words, these two are out of phase. Okay? But the probability of finding an electron, however, is still maximum at both places because probability is not related to the wave function, but it is related to the square of the wave function. So even if the wave function were to be negative, you still will have a positive value, which means that there is a probability of finding electrons. Does that make sense to you?
Yes, thank you.
That is true for all the orbitals. Whenever you see a positive and a negative, some of you may be wondering, why do we even use these signs? These signs are very helpful when you are bringing the atomic wave functions of two electrons between two different atoms, right? Suppose if there is another electron and if it also has positive and positive, when you bring these electronic wave functions together, there is going to be a constructive interference because they are in phase. On the other hand, if I have an electronic wave function where there is a negative here and a positive there, can you see that on the board? Okay, now if I try to bring them, there is not going to be any constructive interference. In other words, there will be no bonding between those electrons if the wave functions are out of phase. That is the reason why we use the wave functions and the signs. Okay, it becomes really wonderful as we get into the molecular orbital theory. That is when we will be using the signs of the wave functions and the importance in constructing the bonding and the anti-bonding orbitals. You must have heard the word anti-bonding, right? So when you bring two electrons together, there are two possibilities, or in fact, there are three possibilities. One is a bonding, in which case you have plus and minus, plus and plus. You may have an anti-bonding, which is a plus and a minus, or sometimes there could be a case where you may have non-bonding interactions. That is when you have the orbitals which are completely orthogonal to each other. That is 90 degrees to each other. There is no way they can overlap. So that is neither bonding nor anti-bonding. So we call that non-bonding situation. Okay? We'll talk a little bit more about when we talk about the molecular orbital theory, MO theory, and give you the introductions. Thank you for asking that question. Are there any other questions, folks?
Professor Chari?
Yes.
Could you go over again with the plus and minus of in phase and out of phase?
Okay. The plus and minus basically are telling you whether the wave functions are in phase or out of phase. I'll give you maybe a little more detailed example here. Let's say if I have a wave like this. Can you see that wave on my board? Okay, and then I have another wave right next to it like this. If I now try to bring the wave functions, as you can see, this is plus, that is plus there. The depression here, right? The trough of the wave, I call that negative and a positive right here. So if I try to combine these two waves, they are in phase, which means they are plus both sides. So a net thing will be like this. Can you see this, Hannah? So that's what I mean by saying they are in phase. All right. Now let me show you when things can be out of phase. I'll give you now another example. Similar wave, except I have something like this. Right? Now this is positive and that is negative here. They're out of phase by 90 degrees. Would you agree with that? Now if I try to combine, the positive combines with the negative, right? That nullifies. The negative combines with the positive. Again, that becomes 0. And that positive combines with this negative. And the net thing is you have absolutely no bonding here. That is what we mean by plus and a minus. Hannah, would that make sense to you?
Yes, it does. Thank you.
Okay, great. Well, this is the opportunity for you to, for us to discuss about things a little bit in detail so that there will be no surprises in the exam. Again, those of you who joined late, if you want to join by video, you're most welcome. Although I cannot force you, but if you are comfortable showing yourself, I would really appreciate that, because that will give me some idea about whether you're in the class or not, whether you're listening to my lecture or not. All right. But again, I'm not forcing you, but I would recommend that you turn your video on if at all possible. Thank you very much. All right, folks. So basically, for those of you who have been looking at my lectures, the last 2 lectures that I have uploaded related to what we call the atomic properties and the electronic configurations. Did you guys get those 2 presentations? How to write the electronic configurations of the atoms. I mean, that's basically a revision of what you must have learned in Chem 1. There is nothing new to that. But this time we go a little bit in detail about what exactly is Hund's rule of maximum multiplicity and the Pauli's exclusion principle and the Aufbau principles, and why the orbitals switch between the fluorescent 3D for the first row transition metals, right? So those are all the things that we discussed. Any questions on this? Are we okay so far? All right, so to summarize what you have been learning, we looked at the electronic configurations of the atoms. We know how to find the unpaired electrons in the atoms. We also emphasize that when you are writing the electronic configurations of transition metals, please keep in mind that when you remove the electrons from transition metals, the first electrons that will leave are your 4s electrons. For example, if I were to write the electronic configuration of, let us say, titanium 2+. Sometimes the question in the exam may be, how many unpaired electrons titanium has? Right? Titanium 2+ has, for example. So to answer that question, you have to start with the electronic configuration of titanium. So when you write the electronic configuration of titanium, it's going to be argon 3d2 4s2. Can you all see the board? Argon 3d8 4s2. All right. Now, when you want to make a dipositive titanium, you must remove 2 electrons. The question then is, which electrons will go, or the 3ds or the 4s? Okay, without exception, when you are removing electrons from transition metals, it is the 4s electrons that will be removed. So what that tells you is, the electronic configuration of titanium 2+ is going to be argon 3d2, not argon 4s2. Okay? Although 4s electrons occupy first, the way they go is slightly different. So this is true for all transition metals. There are no exceptions. All right? So how many unpaired electrons we have in titanium 2+? In a 3D subshell, we have 5 orbitals. Remember the orbitals, we talked about that in the lecture. In the 3D, we have 5 orbitals. These orbitals are dz squared, dx squared minus y squared, dxy, dyz, and dzx. We talked about the shapes of those orbitals too. So when you have 2 electrons, the Hund's rule of multiplicity tells us that those 2 electrons must be placed in different orbitals of the subshell. Okay, it doesn't matter whether it is dx squared minus y squared or dz squared. The reason for that is all these orbitals have same amount of energy. In other words, they are degenerate orbitals. The word degeneracy means they have the same energy. So we have 5 degenerate orbitals in the 3D subshell. I hope you are watching my language very carefully. The precision is very important. Once you understand, then there is no scope for any confusion. So the answer for that question is titanium will have 2 unpaired electrons in titanium 2+. Okay. If you were to do differently, if you were to remove the 4s orbit, the 3D electrons, then you will have a configuration which is not correct. But then that comes as 4s2. In 4s2, how many unpaired electrons we have? 0. So writing the electronic configurations correctly is very important. In fact, this has been experimentally verified that in the case of titanium 2+, we have 2 unpaired electrons, which tells us that it has to be the 3d2. This is 3d2. That's the correct configuration. Am I clear here, folks? Let there be no confusion. There are no exceptions to this. It is the way it happens in all transition metals. Okay, so that's what we kind of summarized in the electronic configurations. Once we know how to write the electronic configurations, then we can also write down the effective nuclear charge of the electrons. Remember that stuff? I gave you some examples of the calculation. So you can also find some more examples on the internet if you look for sample calculations using Slater's rules. So if you want to have, you know, more and more examples, you can always look for them on the internet. But I gave you 1 or 2 examples to teach you how to calculate the effective nuclear charge. Once I know the effective nuclear charge, I can find the energy of that electron, because the energy of any electron is Z squared, Z effective squared. So effective nuclear charge divided by the n squared value, where n is the principal quantum number of that electron. So once you know how to calculate the Z effective, you can calculate the energy, because the energy of the 1s electron of hydrogen is 13.6 electron volts. So if you now take the ratio on both sides, you will then be able to calculate the energy of any electron in an atom. So that is the most powerful thing about Slater's rules. If you ask me, are the Slater's rules perfect? No, they're not, exact, but they are very close to being perfect. Okay? So basically what you have learned now is, given any atom, doesn't matter how many electrons the atom has, you have a tool now that allows you to calculate the energy of every single electron of that atom. Isn't it wonderful? For example, titanium has 22 electrons. And if you want to know the energy of each of those 22 electrons, you can set up your Slater's rules for each electron and use this equation here and be able to calculate the number. So please review the Slater's rules and make sure that you practice some unknown problems and then see if you're getting, if there are any questions, of course, I'll be more than happy to go over that one more time.
Professor Chari?
Yes.
So there was a couple examples you did do in the slides of Slater's rules with like a valence electron on oxygen with doing sigma and Z effective. Could we do an example like that? Because I was confused with how you like knew what to multiply by to get your sigma value.
Which example are we talking about? Is it the oxygen that you're talking about?
Yeah, it was a valence electron on oxygen. And
we will do valence electron of oxygen very quickly, how to set it up, right?
Okay.
All right. So to begin with, what we do is we start with the electronic configuration of oxygen. Oxygen is 1s2, 2s2, 2p4, correct? Yeah. There are 8 electrons in the oxygen nucleus. So the atomic number of oxygen is 8, correct? Now, to calculate the effective nuclear charge of the 2p electron, what we need to do is, we need to take the atomic number, subtract from that the shielding parameter sigma, correct? So to solve this problem, I already know the value of Z, which is 8. I need to calculate the sigma for this. Now I have given you the rules for calculating the sigma for the electrons in 2 categories. If an electron comes from S or P subshell, there are 3 rules. If it is come from D or F, it has different rules. In this case, we are dealing with a P electron here, correct? Okay, so now, if I look at the electronic configuration, the electron under question here is the valence electron, and in this second shell, I have a total of 6 electrons, correct? I have 6 electrons in the valence shell, 2 electrons in the inner shells. So Slater's rules tells us to calculate the sigma, you need to look at how many electrons are there. The total is 6, but you are trying to look at the energy on 1 electron. So if you are looking for one of those electrons in the 2p subshell, you must understand that there are 5 other electrons working on this electron. So you take 5, and then if it is in the same shell, what is the rule there? It's 0.35, correct? Remember the rules? So we have 5 times 0.35 plus electrons in the shell below it, one below it, contribute about 0.85. So there are 2 electrons, so 2 times 0.85. So what is the value here? 5 times 0.35 plus 2 times 0.85. Can anyone quickly calculate and tell me? I don't have a calculator.
Sorry, where'd you get that that decimal from? You went kind of fast there.
Huh?
Where'd you get that decimal from? The Like the 0.85 and
0.85. If you look at the rules of the Slater's rules tells us if you are dealing with an
Oh,
electron from
okay.
S or P subshells, all the electrons in the same shell contribute 0.35 and the shell below will contribute 0.85. And if you were to have electrons even n-2 or lower, they all contribute 1.0. Okay.
Oh, okay.
It's 3.5,
What is the value here?
3.5, 3.45, sorry.
3.45?
Yes.
I want to make sure that, that's what everybody gets, 3.45, okay? Then your Z effective here will be 8 minus 3.45. That is 4.55, right? Okay, so we know now the effective nuclear charge felt by the 2p electron of oxygen in a neutral oxygen atom is 4.55. What does this tell you? It tells you, although you have 8 protons in the nucleus, this electron does not feel the positive charge of all the 8 electrons, or all the 8 protons. It only feels 4.55. The reason for that, we talked about that, is because of the shielding. So these electrons will shield the nuclear charge and transmit only a fraction of it to the outer shells. That makes sense to you folks?
Tari, so with the 4.455, is that for the one electron,
That's correct.
the valence electron?
In fact, if you take any of these electrons here, right, of the 6 electrons, right, they all will have the same effective nuclear charge, 4.55.
Okay, thank you.
So once you know that, you can calculate now the energy of that electron too, right? To calculate the energy, what you do is you set up the equation, energy of the 2p electron and 2p electron of oxygen and energy of the 1s electron of hydrogen. You set up the equations, both are proportional to Z effective squared divided by N squared. This is also Z effective squared divided by N squared. And that comes to, we just calculated the effective nuclear charge of the 2p electron, that came to 4.55. So 4.55 squared divided by N squared, where N is the shell number, right? It's a 2p electron, so that's going to be a 2p electron. And this one here is 1 squared divided by 1 squared, because hydrogen has only 1 electron, right? So we know this one is equal to 13.6 electron volts, right? So if you take the ratio of these two, so you will get energy of oxygen 2p divided by 13.6 electron volts, that is energy of the 1s electron of hydrogen, should be equal to 4.55 squared divided by 2 squared. So the energy of 2p electron of oxygen then will be 13.6 times. Can anyone tell me what the value of 4.55 squared divided by 2 squared?
5.17.
How much?
5.17.
5.17. So that's about 5.17. So what's the answer?
70.4.
How much?
70.4.
70.4. So what is this telling you? Basically, it's telling you that the 2p electron of oxygen is held almost 5 times stronger than the 1s electron of hydrogen. That's what it means. Because 13.6 times 5.17, right? So that 5 tells you how strong it is being held. So it's 5 times stronger than the electron of the hydrogen. So which one is easier to remove? Hydrogen 1s electron or oxygen 2p electron?
The hydrogen.
The hydrogen.
The hydrogen can be easily removed because it's only 13.6 as opposed to 2p of electron. So that's why ionization of oxygen to make O+ is difficult, because the 2p electrons are held 5 times stronger than the hydrogen 1s electron, For that reason, oxygen does not make cations. So you can infer so many things here. If you start looking at this, it tells you, it answers so many questions that you may have from Chem 1. Why doesn't oxygen make cations? Why only metals in the left-hand side of the periodic table make cations? Now it tells you that those numbers speak for themselves. Now, am I making, is that convincing or is it confusing?
It's convincing.
Okay, thank you.
Yep.
Okay, so please follow those things and make sure that you get all the answers. The second thing that we also talked about in this thing is, once you know this, the size of an atom, right? We said with few exceptions, the size of an atom generally increases. There are no exceptions as far as going down, but from left to right, the size of an atom decreases. So it increases here, decreases there. Okay. So if you look at elements such as boron, aluminum, gallium, indium, thallium, so on and so forth, right? If you go into the details, here is what happens. When you go to boron, it's, let's say it's about 0.88 nanometers. And once you go to aluminum, it is 1.43. In fact, it's not nanometers, it's in angstroms. So what should be the size of gallium then? I'll give you one more example too. Keep thinking about this. If I have chromium, molybdenum, and tungsten, okay? Chromium, let's say, is about 0.76 angstroms, and this is 1.66 angstroms. So what should be the size of tungsten then? They are in the same group. What do you expect the gallium to be? Bigger or smaller or same size?
Bigger.
Bigger, right? Same thing with
Yes.
chromium, moly. So can anyone guess? Chromium is 0.76, moly is 1.66. So based on that, what should be the tungsten here?
2.66. 2.76.
2.77, that's what you expect, right? From the trends. If it uniformly increases. But I'm going to tell you something that will, yes. Hannah.
Is gallium special? Like, does it not increase with it?
Yeah, we'll get to that point. Yes, we'll
Okay.
get to the gallium. Let me first answer the tungsten question and then we'll go to the gallium.
Okay.
All right. So, are you guys ready for the reality, folks? This is what you expect, 2.77, based on the extrapolated value, but that's not what happens. Tungsten is only 1.68 angstroms. What is this telling you? Something is going on here. The size is not simply proportional to the shell numbers. In other words, the size increase is not in line with an extrapolation. So this reduction in the size compared to the theoretical expected value is what we call the lanthanide contraction. We talked about that in the lecture too. Why does this happen? Very simple. When you go to chromium, you have only 3D orbitals. When you go to moly, it is 4D. In the tungsten, you have 5D. And also, there are 4f electrons. In tungsten, there are 4f electrons and 5d electrons. We know both D and F have very high angular momentum. As a result, what happens is these electrons, in F we have 14 electrons, in D we have 10 electrons, all these electrons try to stay away from the nucleus. Remember, higher the angular momentum, higher the centripetal force, so they cannot approach the nucleus, so they go away. When the electrons go away from the nuclear charge is now transmitted to the higher shells. So the electrons, the outer shell electrons of tungsten experience very strong force because of the poor shielding of 4F and 5D. And for that reason, those electrons are sucked closer to the nucleus, resulting in a shrinkage or a contraction. That contraction is basically called lanthanide contraction. It's also seen in the boron, aluminum, and gallium. In the case of gallium, it's even more severe. Gallium is still smaller than aluminum. That's not what you expect, right? Size going up. No, that's not what you expect, but that's the fact. So we explain all these variations, that reduction in the size as opposed to what is expected based on the extrapolated values is because of the poor shielding of the D and the F electrons. Okay. Am I making sense here, folks? The reason why we call this lanthanide contraction, some of you may want to know, is because when you look at the lanthanide elements, remember the lanthanide elements down in the periodic table, the lanthanum, cerium, all that stuff there, neodymium, samarium, europium, hafnium, and all that stuff, that's entire series of lanthanides. As you go from lanthanum to lutetium, there are 14 elements in between, the size progressively decreases. Why does this decrease? Because when you go from lanthanum to lutetium, you are populating the 4F subshell. And the 4F is not a good shielder of the nuclear charge. So those electrons generally stay away from the nucleus, and you are increasing the nuclear number or the protonic number of the nucleus. So you're increasing the positive charges and adding electrons that cannot shield the nucleus. So the nuclear charge is transmitted. So there is a progressive decrease in the size going from lanthanum to lutetium. And that's the reason, that's the first time people have observed. So that's why they call the lanthanide contraction. And then when they verified to see if that is true in the other parts of the periodic table, they found out, yes, it is. It is just not limited to rare earths, although we call that a lanthanide contraction. Am I making sense here, folks? Hannah, please go ahead.
Could you quickly go over the concept of shielding and deshielding? I got a little confused with that.
Okay. The shielding and the penetration, right? Penetration, shielding, these are all similar terms. Basically, what we're trying to tell you is, remember the angular momentum, right? L times L plus 1 times H over 2 pi. That is the angular momentum of any electron in any subshell. Okay? If you have S subshell, the L is 0, so the angular momentum is 0, right? For the P subshell, L equals to 1, right? So that would be square root of 2 times H over 2 pi. So when you go to the D subshell, L equals to 2, so that's going to be square root of 6 times H over 2 pi. When the angular momentum increases, right, there is a centripetal force. That means these electrons cannot go closer to the nucleus, but they stay away from the nucleus. When they stay away from the nucleus, they cannot shield the nuclear charge as effectively as an electron that stays in subshells that have lower angular momentum. Okay, so if you have S or P, they can go close to the nucleus. When the electrons go close to the nucleus, they neutralize some of the positive charge going to the outer shells. That is what we call shielding. Shielding is basically neutralization of the positive charge in the nucleus. Hannah, would that make sense?
Yeah, it does. Thank you.
Good. Are there any questions, other questions? This is the time to discuss because Please do not plan on learning everything the day before the exam. I think we talked about that in the beginning. So let's continue with this a little bit more. The size anomalies, that's Lance-Ride contraction. And we also talked about the ionization energies, right? Or the ionization enthalpies. Basically, we said as you go down the group, the ionization energy decreases, the IA decreases, and when you go from left to right, it increases. With few exceptions. So this is the general trend. The exceptions come in, let's say if I have carbon, nitrogen, and oxygen, right? So if you go from carbon to nitrogen, what should happen to the ionization energy? It should increase, correct?
Yeah.
Yeah? So because we said it should increase, that is correct, it increases. But when you go from nitrogen to oxygen, there is a small decrease, not an increase. That's an exception. And why does this happen? So if you look at the electronic configurations, especially the valence shell configurations, carbon is 2s2, 2p2, nitrogen is 2s2, 2p3, oxygen is 2s2, 2p4. If we draw the p subshells for all three of them, there are 3 orbitals in p subshell. For carbon, there are 2 unpaired electrons because it's 2s2, 2p2. In the nitrogen, we have 3 unpaired electrons. This configuration is exchange stabilized because it has high multiplicity. When you go to oxygen, suddenly what you have is you have a pair there. That extra electron that you add to oxygen is not happy. It is feeling a repulsion from this electron. As a result, it becomes easier to remove that electron. For that reason, we see an anomaly. So once you understand, then it's not an anomaly. It is expected. So when people looked at the values and suddenly found, oh, oxygen has an ionization energy lower than nitrogen, that is against the general trends. So whenever you have an element behaving differently than what you expect, then immediately go back to the electronic configuration, see what is changing there. In general, half-filled shells are much stable. Once you remove that half-filled status to give you a pairing always introduces some anomaly because of the electron-electron repulsions. But once you go to fluorine, it again increases. Why does it increase? Because going from oxygen to fluorine, you're also adding a proton in the nucleus, right? Oxygen has only 8 protons, fluorine has 9 of them. So the 9 protons will have a very stronger force acting on the electrons, so it becomes difficult to remove those electrons. So the anomaly comes only when you have just crossing those lines from a half-filled to more than half-filled. At that boundary, you see an anomaly. All right, so these anomalies have to be done. And you also have to keep in mind that there are successive ionization energies, right? IE1, IE2, IE3, we talked about that in the lectures. So in general, the second, third ionization energies are going to be successively larger than the first one, right? Because when you make the first ionization energy, that's the energy of this reaction, delta H for this process, removal of the first electron. When you are removing the second electron, now you are removing electron from a species that's already positively charged, so it's going to be difficult. So the IE1 is always smaller, IE2 is bigger, IE3 is even bigger, IE4 is even more bigger. And anytime when you have the electronic configuration of any of these ions close to a noble gas configuration, the corresponding ionization energy will be even larger. So for example, if I go from titanium 3 to titanium 4 plus an electron, and let's say titanium 4 plus to titanium 5 plus an electron. Okay, so this is going to be IE4, 1, 2, 3, IE3 here, and this is the IE4. Suddenly this is very large, 10 times more than the IE3. The reason for that is when you go to titanium 4 plus, the electronic configuration is argon. In titanium 3 plus, it's argon 3D1. So when you go to titanium 4 plus argon, so anytime you have an ion whose electronic configuration is that of a noble gas, the removal of an electron from that ion is extremely difficult. So just to give you, for the sake of argument, for the titanium, IE1, let's say, is 1,000, IE2 is 2,500, IE3 is 4,700, that is titanium 1 plus, that is the 2 plus to 3 plus, 3 plus. So this is IE1, that is titanium 2, titanium plus 1 plus electron. This is IE2, titanium plus 1 to titanium plus 2 plus electron. IE3 is titanium 2 plus to titanium 3 plus electron. And IE4 is, let's say, 7,800. That's about Ti3 plus giving Ti4 plus electron. And finally, when you go to the fifth ionization energy, this will be 25,000. You can see that anomaly there. That anomaly, whenever you see that, you know that that process involves removing an electron from an ion whose electronic configuration is that of a noble gas. So sometimes in the exam, we give you these numbers and tell you which element it might be. So when your fifth ionization energy is large, then you know Veer, who has volunteered to record these sessions and share it with all of us. I appreciate his time. All right, the next thing that we need to know is what is called inert pair effect. We talked briefly in the lectures, but let's talk about this. Inert pair effect. You have done almost more than 2 years of chemistry at Rowan. So you must have been exposed to lots of ions, both in organic and inorganic. And if you go back, I don't know if you thought about this very carefully or not, there are certain ionic states that you will never see. For example, if I have lead in 3 plus is impossible. Lead always stays as 2 plus or 4 plus, but not 3 plus. Amazing, right? Have you ever seen any compound in which lead is 3 plus? Or tin in 3 plus? No. Similarly, if I look at bismuth in 4 plus state is never seen. Bismuth is either 3 plus or 5 plus, but never 4 plus. Same thing with thallium. Thallium 2 plus, never seen. Thallium can be 1 plus or 3 plus. That's true with the indium too. Indium, which is an element above thallium, can exist either in a +1 or a +3, but never in a +2 state. So why is this happening here? To answer that question, we need to look at the electronic configurations of, let's say, lead 2 plus. Pb2 plus has a valence electronic configuration of xenon 6s2. Right? Quite interestingly, that is the configuration of thallium 1 plus, same thing. And similarly, bismuth 4 plus is also, lead 2 plus and bismuth 3 plus. Bismuth 3 plus is also 6s2. So what's common between lead 2 plus, thallium 1 plus, and bismuth 3 plus? They all have the same electronic configuration, right? 6s2, 6s2, 6s2. If you want to make lead 3 plus, what do you have to do? You have to remove an electron, one electron from the 6s2. Similarly, if you have to make thallium 2 plus, you have to remove one electron from 6s2. Same thing with the bismuth 3 plus. If you want to make bismuth 4 plus, you must remove one electron from the 6s2. The fact that these oxidation states are not stable tells you something very interesting. It tells you that this 6s2 configuration, either it will stay as a pair or leave as a pair, but you cannot break that pair. In other words, it is impossible to get an electron configuration of 6s1. That inability to break a pair of electrons in the 6s or the 5s shells is generally known as the inert pair effect. So this pair stays together or leaves together, but you cannot break it. That is the reason why you will never see oxidation states such as lead 3 plus, bismuth 4 plus, or thallium 2 plus. You will never see them in the real life.
Is there a reason why they leave as a pair? Like, is there a specific reason why they cannot, like, one at a
They are
time?
so exchange stabilized in these compounds that it is impossible to break them. The same thing applies to carbon too. Carbon is also stable as, carbenes, like carbon in the 2 plus state or 4 plus state, but never in the 3 plus. Not very stable. I'll tell you, maybe in 1973, somebody reported a compound called barium bismuth oxide, BaBiO3. Okay, this is true compound, real compound. So what should be the oxidation state of bismuth here?
Uh, 4 plus.
Huh?
4 plus.
4 plus,
Positive 4.
right? But is bismuth 4 plus stable? We just learned you can't have this. But this is true. This compound, 1:1:3 ratio compound was made. It was pure compound. Are we violating the inert pair effect here? Apparently, that is not what is happening here. What happens here is very interesting. If I double the formula, we have Ba2 and 2 bismuth here and oxygen 6. Now, of the 2 bismuth, one is 3 plus, one is 5 plus. So this is how they explain the formation of BaBiO3. Bi is not 4 plus. It is an average of 3 plus and 5 plus that shows up as a 4 plus in the formula. But the real molecular formula of this is this. That is only an empirical formula. Okay. These compounds are also very interesting because if you put a little bit of lead into this, you can make superconducting compounds. We talked about superconductors some time ago, right? That is the first superconductor based on oxides that shows conductivity about 13 Kelvin. It was discovered by Art Slate of DuPont in 1973. It became a big revolution there at that time. Prior to this discovery, all the superconductors were metals or alloys. So for the first time in an oxide, Art Slate, who is retired now, made this compound that was a big, major breakthrough in science. But basically, the idea is that once you appreciate the inert pair effect, then you can see how the charge imbalances and how the electrons stay together. So this is a very interesting observation. Am I making sense here, folks? Yeah? Maybe I'm giving you a little deeper meaning of a unit pair effect more than what is needed, but it's good to know that these things have real life implications. The other thing that I wanted to discuss today is the concept of electron affinity. I discussed, I think, electronegativity in the lecture in detail, but we never had a chance to talk about electron affinity, which is also an important property, and a property that sometimes might lead to some confusion because the way the book is trying to tell you. So we need to understand. Anyone remembers the definition of electron affinity? Hmm? You all have done Chem 1, right?
I think it's like the energy released upon receiving an electron.
That is precisely what is called electron gain enthalpy, not electron affinity.
Is it how much an atom wants to keep the electron, like the energy?
It's a little complicated. You have to first understand the very meaning of affinity. What is affinity? Affinity, the root word for affinity is affection, right? Or the love. Now, when you talk about emotional feelings like love and affinity and affection, it's very difficult to scientifically quantify it. So that is where the problem comes. Electron affinity is a measure of how much an atom loves an electron. Okay? So I always tell this example to my students in explaining this electron affinity. I ask them, how do you find out how much affinity I have for chocolate? If you want to know how much I love a chocolate, what is that you can do to quantify it?
Measure how many candies you eat a day.
Yeah. The question is more philosophical, right? You have to get into my mind or measure some response that I have towards my affection for chocolates. So for example, you can throw a chocolate when I'm around and see how fast I run to grab it. At the speed which I go to grab it is perhaps a measure of how much I love it, right? Or perhaps you can show me a chocolate and measure the volume of saliva I produce because I love it so much that I won't really eat it right away. And that could be, that volume could be a measure of how much I love a chocolate. The other thing perhaps you can do is, you can give me a chocolate and then see how difficult it is to get it back from me. Right? If I really love it, I will hold on to it very tightly, right? I will not give it back to you without a fight. That is precisely what we do in the electron affinity of an atom. What we do is we give an electron to an atom and see how difficult it is to get it back. That process, that energy that is required to remove an electron that's already added to a neutral atom is what we call the electron affinity. So let me put this one in writing here. So in the first step, what you do is you take an atom in a gas phase and you add an electron and you make an anion. Right? This is what we call electron gain enthalpy, or sometimes it's called EGE. Okay? People found this EGE for most elements is exothermic, which basically tells you atoms, regardless of their position in the periodic table, they all have some affinity for electrons. Some have more affinity, some have less affinity, but all atoms in general have very high affinity for electrons. This is the observation. Now, but that's not electron affinity, right? What I'm going to do is I'm going to do the reverse of this. So I take the species A minus, which is made by adding an electron to a neutral atom, and try to get back my electron. That one is called electron affinity. See the difference between electron gain enthalpy and electron affinity. So electron affinity, if the electron gain enthalpy is exothermic, this must be endothermic. Am I making sense here, folks? That is the definition of electron affinity. So sometimes the textbook confuses, some books confuse you between electron gain enthalpy and electron affinities, but the people like Linus Pauling, who were the first people who put the concepts, this is what they had in mind, to see how difficult it is to remove an electron that is already added to a neutral atom. Now, in terms of the trends of electron affinity, it's generally electron affinity decreases down the group, and in general it increases. So elements such as, like hydrogen, lithium, sodium, potassium, rubidium, and cesium, if you look them in the periodic table, the cesium has least electron affinity. Similarly, if you go from left to right, you have increase in the electron affinity. Okay? But there are small discrepancies here and there. So we will see those discrepancies. But let's say if you have carbon, nitrogen, oxygen, and fluorine, right? So what should be the electron affinity like? If you go to carbon to nitrogen, is the electron affinity should be more or less?
More. More.
From the trends, you would expect the electron affinity of nitrogen must be greater than that of carbon. But that's not what people see. In fact, nitrogen is one of the elements which has very small electron affinity. The reason for that is, again, back to the
Partial orbital.
electronic configuration, right? Remember, nitrogen has 3 electrons in the 2p subshell, right? They are exchange stabilized. Now, if I give an electron to nitrogen, what happens?
It will be unstable.
When I put an electron here, there's going to be electron-electron repulsions, right? So the nitrogen tells me, no, I don't want an extra electron. I'm happy the way I am. So for that reason, nitrogen shows an anomaly. But when you go from nitrogen to oxygen, the electron affinity increases. Oxygen to fluorine, the electron affinity increases too. So carbon to nitrogen, there is a small anomaly. So let's talk about another anomaly. Let's say I have lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon, right? So we expect an increase here. So if you go from lithium to beryllium, which one should have higher electron affinity?
Beryllium.
From the trends I'm showing you, of course, beryllium should have higher electron affinity, but that's not what people see. Beryllium has slightly lower electron affinity compared to lithium. Why? Here again, we have to look at the electronic configurations.
Isn't beryllium one of those?
Hmm?
Isn't beryllium one of those elements that can have 2 charges, even though it's not like a transition metal or something?
That could be one reason, but the most obvious reason is as follows. When you go to lithium, right, it is 1s2, 2s1. In the case of beryllium, the valence electron configuration is 2s2, and boron is 2s2, 2p1, so on and so forth. If you look at beryllium, it's 2s2, right? When you add an electron, where would that extra electron go?
The p orbital.
The p orbital, right? So which one has higher nuclear, which one has more stable configuration? Is it s electrons or p electrons?
S electron.
S electrons, because they have no angular momentum, they are more stable because they can reach the nucleus and get stabilized compared to 2p. For that reason, beryllium doesn't want that extra electron because that extra electron is not as stable as you go from lithium to beryllium. Okay, so anytime you see an anomaly, it is always a good idea to write down the electronic configurations and argue from that point of view. Am I making sense here, folks? Of course, you are going to go back and practice these things and look at the numbers and try to make some sense about all these anomalies. I'm sure you must have not have seen all this stuff in Chem 1, some of you at least. So it's a good thing because all these are the pillars of inorganic chemistry. The foundations of inorganic chemistry lies in the atomic properties. That's the reason why we are going to great lengths in explaining all these small details of elements in the periodic table. You won't see these details in any other course in chemistry, whether it is quantitative analysis or whether it is biochem or organic chem. We will not discuss other elements here. It can be slightly frustrating because you're dealing with so many of them, unlike 3 or 4 elements that you do in organic. But these elements are there and they're very useful and you have to live with them. In order to live with them, it's better to understand them. That's what we're trying to do in an organic, all right? Any other questions, folks? Somebody sent me a note saying that how do people calculate the electronegativities? Okay. Remember, fluorine has 4.0 electron affinity. Highest electron affinity, electronegativity is 4.0. But before I go to the electronegativity concept, let me show you one more anomaly here. If you go to fluorine to chlorine, right, to bromine, what should electron affinity be like? Which one should have highest electron affinity?
Fluorine, but it's the opposite. I think chlorine has more.
Correct. Sahil, is that what you answered, fluorine?
Yeah.
Okay. I'll tell you again a small anomaly. Yes, you would expect fluorine to have highest electron affinity, but
You do smaller size, I think.
It is the chlorine that has the highest electron affinity in the periodic table, not fluorine. See how generally, 98% of the time the trends are good, but occasionally you get into the small anomalies. So how do we explain this?
Smaller size.
Yeah, smaller size of fluorine and putting more electrons. So if you look at fluorine, it is 1s2, 2s2, 2p5, right? Yeah. And if you look at chlorine, it's going to be neon 3s2, 3p5. The capacity of the second shell is 8. The capacity of the third shell is 18 because third shell is larger. Remember the rule of 2n squared, right? 2n squared tells you the capacity of any shell. If you look at the second shell, 2n squared is what? 8, right? So that's the total number of electrons second shell can hold. Third one, 2n squared is 18. It can add 18 electrons. Now, if I add an electron to these two, this is a very small space here. Second shell does not have the real estate the third shell has. It's a small footprint. So when you put too many electrons, the electron-electron repulsions contribute to slightly smaller electron affinities of fluorine. On the other hand, if you add it to chlorine, these electron-electron repulsions are not very high because it has a much larger space. So when you increase that space, you minimize the repulsions. And for that reason, chlorine has higher electron affinity. Okay? But electronegativities wise, fluorine has the highest electronegativity. That is for sure. And there was the question about how do people calculate the electronegativities according to Pauling's scale. Okay, let me do that very quickly, taking an example. Let's take HF as an example. Okay, Linus Pauling summarized that of all the elements in the periodic table, fluorine has the highest electronegativity, and he called the electronegativity of fluorine as 4.0. That is the maximum, just like your GPA, right? 4.0, the best students get 4.0. So Pauling, being a great teacher, he said, well, let's give fluorine 4.0. Grade A, right? So that's easy to remember. Now, if you want to calculate the electronegativity of any other atom, such as hydrogen in this case, what Pauling said is, do this first. Look at H2 plus F2, 1/2 of this, 1/2 of this, giving HF, right? So the delta H for this reaction basically, right? Basically, you're breaking 1/2 of hydrogen-hydrogen bonds, you're breaking 1/2 of fluorine-fluorine bonds, and you're breaking one HF bond, correct? So let's look at the bond breaking here. This is 1/2 of the hydrogen-hydrogen bond energy is about 436 kilojoules per mole, plus the fluorine, the bond energy is about 158. Okay. So what is that value? Can anyone quickly calculate that?
$594.
Huh?
594.
594 divided by 2, right? 1/2 of it.
297. Sorry.
297. Okay. So if everything is ideal, this should be the bond length of bond strength of HF2. But if one is more electronegative than the other, there is going to be additional interactions that will change those numbers. So let's look at the difference in the bond energies between what is experimentally known and what is theoretically calculated. So that is the bond energy that we get experimentally minus bond energy that you get theoretically. So experimentally, people find that it takes about 566 kilojoules as opposed to the theoretical value of 297. So that difference in the electronegativities is about 269 kilojoules. Okay. Now what Pauling said was the difference in the electronegativities of fluorine and hydrogen should be equal to 0.102 times square root of this delta HF. That is the difference in the bonding energies of theory and calculated values, which is 269. 0.102 times square root of 269. And when you do that calculation, you get approximately 1.67. Some of you may be wondering, what the hell am I doing with 0.102? The 0.102 is a conversion factor from kilojoules to electron volts. Okay, so that's what the conversion factor is. So that difference is 1.67. So if I know the difference is 1.67, and I know that fluorine is 4, so what should be the electron negativity of hydrogen then? That should be 4 times minus 1.67, right? So that should be 2.32. Okay. that difference, so this is how you calculate the hydrogen electronegativity. Using the hydrogen electronegativity, you can then look at HCl, do the same calculation. Now that you know the hydrogen, you can calculate the chlorine, and the electronegativity of chlorine comes to about 3.2. Fluorine generally makes compounds with most of the elements in the periodic table. It's the most reactive element in the periodic table. So that's how Linus Pauling was able to look at several fluorides of the metals in the periodic table and the non-metals, and was able to come back to this conclusion here. And he developed a table of electronegativities. In the PowerPoint presentation, I think I also talked about Allred-Rockhouse scale, Mulliken scale of electronegativities, right? Is this clear to the person who has asked me this question? How do people calculate the electronegativities? Right, so the last thing that I have only 2 or 3 minutes, I'd like to wind this chapter off, is talk about hardness and softness. Elements in the periodic table, especially the atoms of the elements in the periodic table, can be classified into 2 different types, either as hard or soft, depending on how polarizable the electron clouds are. In general, when you go down the periodic table, as the size of an atom increases, it becomes soft. On the other hand, smaller atoms tend to be hard. Okay. Similarly, when you go from left to right, the elements on the left tend to be soft, and on the right, they become hard. Hard and soft can be realized in a simple thought experiments. Most of you must have seen the soap bubbles, right? People can blow bubbles. You can make small bubbles, or you can also make large bubbles, right? Which ones are nearly spherical? Small ones or the big ones?
Small ones.
The small ones are nearly perfect and the big ones are lopsided, right? So in other words, the small ones are hard and the big ones are soft. In other words, the electron cloud is not symmetric around the nucleus. For a soft atom, the electron cloud is lopsided. So for example, instead of being a sphere, it is something like a distorted sphere. That distortion increases as you increase the size. So people have defined the hardness factor as 1/2 of ionization energy minus electron affinity. So if you know the ionization energy and the electron affinity, that difference divided by 2 is defined as the hardness. So harder atoms tend to have very high ionization energies and very low electron affinities. Okay? So if you now go, as you know, elements on the top generally tend to have very high ionization energies, and they are also smaller, and for that reason, they're also harder. Am I making sense here, folks? Okay, so go back and read a little bit about the hardness and softness. I'll also put that stuff today in the thing, and that's about the time we have. And again, coming week, I'm going to put some lectures on the chemical bonding. I want all of you to please review your skills of writing Lewis structures, the resonance forms from the Chem 1 class. If you look at my syllabus, right, these are some of the expectations I have coming into this class, so that I don't want to spend 3 weeks talking about Lewis structures. Okay. So it's a good time for you to go back, review how to write the Lewis structures, the formal charges, the resonating structures. Right? Once we know, then we'll try to talk a little bit about the hybridization, and then we'll talk about some issues about why hybridization sometimes may not be Perfect. And then we'll move on to what we call the molecular orbital theory, especially for simple diatomic molecules. So that will be the plan for the next week. That kind of helps you to prepare for the lectures and you know what to read. Any other questions, folks? If not, I wish you all a pleasant week and a great weekend too.